Hi students, good evening. So today we are going to start one of the very important chapter for the JEE mains and JEE advance. So the Newton's laws of motion, work power energy, and system of particles and rigid body motion. So these topics, right, they are considered as the core mechanics. And not just that, this is important from a weightage point, but even some of the things that we'll discuss, some principles we'll discuss in the laws of motion chapter, right, we'll keep using them, especially in the JEE advanced when you have questions coming from cross topic, right, like some of the principles in the laws of motion, they can be linked to say problems in electrostatics based on the +2 syllabus. They can be linked to magnetism, and they can be linked to even optics. So we'll see some problems when we go to the respective chapters. So especially in JEE advanced, right, we have scope for getting questions like that. Okay, so in that way, this is going to be one of the very important chapters, not just because of the weightage that the core mechanics has in the JEE advanced or even JEE mains, but because it is also related to the other topics, right, we can have cross topic questions and all these laws of motion principles, right. Especially we'll talk about two principles. One is this conservation of momentum principle, and second is going to be the conservation of energy. Of course, that comes in the next chapter. So these two principles, right, we'll keep using quite often in case of other topics also. Okay, so we'll get started with the discussion. So first we'll begin with the introduction to the idea of laws of motion. So what is it that we are going to study in the laws of motion? So what are we going to learn? Because we are straight away coming from where? We are coming from the kinematics, right? So in kinematics means what? This also we have studied in split. 1D motion, 2D and 3D, which we are calling as what? The general motion. Okay, so this is what we were looking at in kinematics. So kinematics, mostly what is it that we have studied? We have studied about the parameters of motion. So what is it that we have studied in this case? We talked about the parameters of motion, like displacement, initial velocity, final velocity, acceleration. So relation between these parameters is what we were focusing on in kinematics. Okay, what is it that we are going to learn in the Newton's laws of motion? So if we look at the laws of motion, right, it is going to give us the other side of the picture. Like, what we have been doing in kinematics is what we were looking at the parameters of motion, whether it is the distance or displacement, speed, velocity, acceleration, the journey time. We're trying to understand the relation between these parameters. Okay, so here when you look at motion, the cause of motion or the cause of change in motion is basically what we are going to understand in this laws of motion chapter. So how the motion of the object can get changed, okay, or how we can actually create motion in the object, and how we'll be able to change the motion of the object or create motion inside an object by force. So if there is a force, means there will be motion that can begin, and the motion can also be changed by the force. So how and all we'll learn in this chapter. If there is no force, then what is going to be the situation? So we'll try to understand the other side. So kinematics, we have talked about the parameters of motion, the relation between them. If you look at what is the cause for the motion to happen or cause for the change of motion, that basically arises from the force. So we are going to study in detail about how the force is going to cause motion or cause change in motion, and what are the other things that we can study in terms of the force affecting the motion of the object. Okay, so we'll study in detail about this in the laws of motion chapter. Okay, now when we are looking at the laws of motion, right, we are going to be focusing on one type of motion, what we call as translation motion. So what is this translation motion? So if you look at a body, like look at this wheel, no, how is the wheel moving? It is moving on the flat surface. But if you take a closer look at the motion, right, you see one thing, the wheel is not rolling. Normally what we observe, the wheel will roll, but here in this representation, right, the wheel is not rolling, a wheel is just moving like that. So if you look at any particle or any point on that wheel, you will see that any point in a given time, right, will be covering the same displacement. If it is covering the same displacement in a given time, means what? They will be having the same velocities. You take any point on the wheel, all of them are going to cover the same displacement in a given time, means they will be having the same velocities and they will be also having the same accelerations. This type of motion, right, is what we call as translation. So what is translation? Understand clearly. If you have a body, like an object is like this, it is just moving in such a way that any part of the body you take in a given time, any part of the body is going to have the same displacement covered, and also any part of the body will be having the same velocity, okay, and they will be having, of course, same accelerations. Such a motion of the object, right, is what we call as translation motion. Now you may ask, what is the other type of motion? Other type of motion we will study in the rotation motion of the rigid body. Look at the fan. What is the fan doing? We will say the fan is actually rotating. What do we say? The fan is rotating. So when you look at the rotation of the fan, take one wing of the fan. Okay, so this is the axis. This is what we call as the axis of rotation. So a rotating body will have an axis about which, like in this case, you can see this is the axis, right, about which the fan is rotating. You look at it now. I mark a point 1 and I'll mark another point 2. If you see, the point 1 is going in a circle, point 2 also will go in a circle, but the difference is what, point 1 is going in a circle of smaller radius, point 2 is going in a circle of larger radius, means their motion is different, right? Their motion is basically different, but in this case of rotation, we'll see somehow they will be related. So when we go to the rotational motion study, we'll discuss what is the relation between the particle 1 and particle 2, their motion, the relation between the motion of particle 1 and particle 2. What is it? We will understand when we go to the rotational motion. But here clearly, what are we able to observe? The distance covered by these particles, right, is not same. Particle 1 is going in a circle of small radius, particle 2 is going in a circle of larger radius. So this is not the translation motion. Even if you take the wheel which is rolling, right, so here this wheel is what? This wheel is just having the translation motion. Rolling, we will study about it in same rotational motion chapter. Rolling is going to be a combination. So if you look at the rolling, of the wheel, right, rolling is going to be a combination of the translation and rotation. Okay, need not worry about it, how the rolling will be a combination of both translation and rotation. We will study about it in detail when we go to the rotational motion chapter. Okay, so here we need to just get the idea of what do you mean by the translation, because in Newton's laws of motion chapter, right, we are going to be focusing on the translation motion. Okay, now when we are discussing the motion of an object, right, remember we keep telling a body is located at the point 1, 2, 3, like that we will give the coordinates. So coordinates represent what? The location of an particle in the Cartesian system. Like we will give the x coordinate, we will give the y coordinate, and we will give the z coordinate. Using that, what we can find? We can find where exactly is that particular object in the space. But the thing is, think about it, right? Any object, when we say it is having mass, it will definitely occupy some volume, isn't it? Because any object having mass means what? It will occupy volume. If it is occupying volume, means how can we say that the object is located at 1, 2, because 1, 2, 3 represents what? It represents a single point in space. It doesn't represent volume. Correct? It doesn't represent volume. So why are we saying that the object is located at 1, 2 and it is moving its position from 1, 2 to 4, 5, like that? So we always use the coordinates, right, to represent the position of the object. What we are doing there? We are making one big assumption. That is what we call as the point mass assumption. This is an important one. What is the assumption we are making? We are making the assumption of what? Point mass. So what is the point mass? It's a theoretical concept. So point mass is supposed to have 0 dimensions. So it will not have any length, no width, no height, means no 0 dimensions. It will be located at a single point. That is why we call it as what? Point mass. And is it really possible to have point masses? It's a theoretical concept. But then why do we use it? We use it because it will actually simplify our calculations in terms of doing the problems. Okay, we know every body will have some volume. But when we talk about the translation, right? Translation motion, what are we saying? Each and every part of the body will move in the same manner. So can we represent the entire body by just one point mass? Okay, so we'll assume that the body is located at a single point. So that assumption is what we call as the point mass assumption. But is it true? No, right? Every body will occupy some volume. But then under what conditions these assumptions could be fair? You know, when we look at the motion of the body, right? We'll either talk in terms of the displacement of the body or the distance covered. If the displacement of the body or the distance covered are much greater than the actual size of the body, let us say the size of the object is in terms of millimeters and the distances covered are either in terms of meter or kilometers. You see, the distance covered is in much higher magnitude than the actual size of the body. Under those assumptions, right, under those conditions, this point mass assumption will be fair. So this will be a fair assumption when the distances covered or the displacements that are measured for the motion of the body are very large in comparison to the actual size of the object. Okay, so if the size of the object is in say millimeter range and the distance covered and the displacement they are in terms of what? A meter or kilometer, then under that conditions, right, this assumption is fair. Okay, so this point mass assumption is one of the important assumptions that we will be using in the case of the Newton's laws of motion. Okay, so that is only when we can say the coordinates of the point. Otherwise we can never use the word coordinates of the point. We can never use the word coordinates of the object. Why? If you have to say coordinates of the object, what are you referring to? Object is going to occupy volume, right? We can never give the coordinates of the object. So when we are giving the coordinates of the object, we are referring to the assumption of the point mass. Okay, so this is an important assumption that we make. And in the laws of motion, right, we are going to study the motion of the object. Okay, so if you look at fundamentally every object, right, has got two states. Okay, so one is what we call as the state of rest, another is what we call as the state of motion. Okay, we have seen the definitions of these two already in the kinematics. Like you look at this ball, initially what state it is in the state of rest. Its position is not changing with respect to time, correct or not? But once this player is kicking the ball, what is happening? The ball is moving, which means its position is changing with respect to time. Then we can measure the distance covered by the ball, we can measure the displacement of the ball, all these things we can measure. Okay, so we have two states. One is the state of rest and second is the state of motion. Okay, so here when we say state of motion, right, we'll consider state of motion with uniform velocity. So when we say motion, right, what are we considering? We are considering the state of motion of the body with uniform velocity. Okay, because if there is nothing that is coming into contact with the body, or if there is no sort of force or anything applied onto the body, then if it is having a particular velocity, right, what do we generally observe? It will keep moving with the same velocity. It will keep moving the same velocity, right? So we'll see about that in one of the Newton's laws. But the idea is when we say motion, right, what is it that we are referring to? It is the motion of the object with a uniform velocity or constant velocity. Okay, so these are the two states that we will look at for any object. Now in the discussion about the laws of motion, the Newton's laws, we are going to talk about these states. Okay, so how a force can impact the state of the object, that is what we will be seeing in one of these laws. Okay, so we'll move on to the next idea of inertia concept. Okay, so once we complete the inertia, because inertia will be related to the Newton's first law of motion. So the concept of inertia is linked to what? The first law of motion. So we need to understand the idea of what is inertia. Before we will get to the inertia concept, right? Let us say there is a object of mass 1 kg which is initially at rest. Take another object 10 kg. This is at rest. Now if you want to move them, this is a very practical thing. You want to move them, so you can move them only when you apply the force. Otherwise you will not be able to move them. Otherwise, without applying the force, you will not be able to move them. Okay. And on its own, the 1 kg cannot move on its own. The 10 kg object cannot start moving on its own. Now you will have a question, sir, what if the 10 kg object is like a motor vehicle or something? Then there is an engine, right? There is a fuel that is used, because of which there is a motion that is getting generated. That is a different story. We are looking at just the objects without any engine or something. Okay. 1 kg cannot move on its own. 10 kg cannot move on its own, which means what? This 1 kg object which is at rest, or the 10 kg object which is at rest, they are not able to change their state on their own. They are not able to change their state on their own. Somebody has to come and apply the force. Okay. Similarly, if you look at a 1 kg object which is moving with some velocity, can it come to rest on its own? No, it cannot come to rest on its own. Now you will again ask questions. I don't know if you just roll the ball on the ground, or you just think of this 1 kg object only. If you move this 1 kg object on the floor, after some time this object will be stopping, right? You will see that the object will be stopping. Does it mean that there is no force acting on the object? It is in contact with the floor, right? The floor is actually acting a force on the object. So the object is on its own. No other force acting is on it. Then the object which is in motion, right, cannot come to rest on its own. Some force should be acting on it. So every body will have this inherent property, by the virtue of which, right, they cannot change their state on their own. State means what? Either we are saying the state of rest or the state of uniform velocity motion. They cannot change their state. And this property that is there in every body, right, is what we call as the inertia. So this is going to be there for every body. Okay. And if you look at what is this inertia? Is it a physical quantity? It is not a physical quantity. The inertia is not a physical quantity. It is just the property of the body. By virtue of it, it cannot change its own state. If it is at rest, means it will continue to be in the state of rest. If it is in motion, means it will continue to be in that state of uniform velocity motion. And on what this inertia property will depend upon. For that, right, let us just again go back to the same example. You have the 1 kg object at rest, 10 kg object at rest. You try to generate motion in them. Where do you find it is difficult to generate the motion? Obviously 1 kg means you will try to just push it with a small force, it will start moving. 10 kg means you have to give a lot of push, isn't it? Means where it is difficult to generate the motion, in the 10 kg case it is difficult to generate the motion. Means this is opposing. So it is at rest. You are trying to create motion. Which body is opposing more? The 10 kg object is opposing more, right? Means we will have to say that the inertia of the 10 kg mass is higher, because that is opposing more to generate the motion or to change its state. So the inertia is measured in terms of what? The ability of the object to hold on to the state. Inertia is measured as what? The ability of the object to hold on to the state. So if the mass of the object is higher, means what? Its inertia will be higher. So inertia is going to be depending upon the mass of the object. Higher mass means higher inertia. Now you will ask, is there a formula like, inertia is equal to something into mass or something into mass square? No, there is no formula like that. Okay. So here we will just quantify the inertia. We are not even saying inertia is equal to mass. We are saying what? Inertia is quantified in terms of mass. Means higher mass means higher inertia. Lesser mass means what? Lesser inertia. And since this is not a physical quantity, right, inertia will not have any unit, and it will also not have any dimensions. It will be a unitless and dimensionless quantity. Okay. So in translatory motion, what is the motion we are discussing here? translatory motion. The inertia of the body is quantified by using what? Mass. Inertia is quantified by using mass. And there is one more interesting thing. This is where a lot of people will have a misconception. Okay, so if you have two objects which are having the same mass, if you are having two objects having the same mass, let us take the example. There is a 1 kg object which is moving with a velocity of 3 meter per second. Another 1 kg object which is moving with a velocity of 5 meter per second. Both are having same mass, but what about the velocities? Speeds are different. Now, generally, what is the thought we have? We may think that, okay, this is having a higher, this is having a lesser velocity, this is having a higher velocity. So we may have a thought that, okay, so this 5 meter per second velocity mass could be having a higher inertia, and the 3 meter per second mass could be having a lower inertia. That is the thought that we will generally get. Because you know why? We will try to understand the inertia by equating it to momentum. So what is momentum? We have some understanding from the lower standards. Again, we are going to discuss about the momentum here also. But generally, you know, same mass, high velocity means what? The momentum of the object will be higher. So some people tend to think that, okay, we can quantify the inertia in terms of momentum. No, inertia cannot be quantified in terms of momentum. Whether the 1 kg object is moving with a 3 meter per second speed or 5 meter per second speed, or even if it is at rest. In all these cases, right, when you want to talk about the inertia, the ability of that 1 kg mass to hold on to its state, whatever is the state, whether it is a state of rest or state of motion, the inertia is going to be only depending upon the mass. Means what? If you have two bodies having equal mass, one is in motion, other one is at rest, both of them are going to be possessing the same inertia, because inertia is going to be only and only depending upon the mass and not on the velocity. So the momentum of that 5 meter per second velocity object is higher, momentum is higher, but inertia is not quantified by using momentum. Inertia is quantified by using what? It is quantified by using the mass. Okay, so this is about the idea of inertia in case of the translatory motion. And why are we discussing about the inertia? Because the inertia is going to be used while we talk about the first law of motion. Okay guys, so let us go on to the Newton's first law. This is also, by the way, called as what? The law of inertia. So what do we call it as? The law of inertia. What is this? A body continues to be in its state of rest or uniform velocity motion along a straight line. Because if the velocity is uniform or constant, means what? It will neither change its direction nor change its magnitude. Means it will continue to move in the straight line. That is why we are adding this word straight line. Okay, a body continues to be in the state of rest or in the state of uniform velocity motion in a straight line unless it is acted upon by some external force to change the state. Means what? If a body is there, okay, so let us say m is the mass of the body. If there is an external force, means its state can be changed. If there is external force, means its state can be changed, but there is no external force, means what? Its state is going to remain the same. Its state is going to remain the same. Okay, so this is what is the concept of Newton's first law. So here, no, the ability of the body to hold on to its state when there is no external force, means it will be able to hold on to the state of either rest or uniform velocity. That is what we are calling as what? Inertia, right? So the Newton's first law is related to the concept of inertia, the ability of the body to hold on to its state of rest or uniform velocity motion. Only when there is a force, there is an external force, then you know the state can be changed. Okay, so this is what is the Newton's first law. Obviously, you know, Newton's first law, we will not have any numerical importance. It's a theoretical idea to understand the concept of inertia. Okay, now before we go to the second law and things like that, we mentioned the word force. Unless there is an external force, it will maintain its state. That is what we said in the Newton's first law statement, right? Let us dig a little bit into the concept of force. Already we know from our lower standards, force is defined as what? The push or pull effect. Force is defined as what? Push or pull. Force can come for various reasons. It may be because of the mass of the object. In this case, what do we call it as the gravitational force? It may be because of the charges on the objects. We call it as what? Electrostatic force. Like that, depending upon what is the reason for the force, we can give the forces different names. But here we are trying to understand the force concept more from the basic definition. So what do we actually call as a force? The reasons for the force is different. If the force is coming because of masses, we call it as gravitational force. If the force is coming because of charges, we call it as electrostatic force, and so on. But here let us try to understand what is actually the force itself. This is what we call as the push or pull effect. Like there is an object, the object is getting pulled or the object is getting pushed. Okay, so the effect that is creating this push or pull, right, is what we call as force. And we can try to understand or define force in the context of this Newton's laws. How? So what is the force actually doing or trying to do? It is trying to change the state of the body. So we can define force as something which produces or tries to produce motion in a body at rest. Means if there is a body at rest, imagine we are applying a force on it. Means what? It will produce motion in the body, or it will try to produce. Similarly, you can also define it like this. The force is something which changes or tries to change the motion of the moving body. Means let us say there is already a moving body. Okay, so there is already a moving body with some uniform velocity. When you apply a force, it changes or tries to change the motion of the body. Means the velocity might increase in terms of its magnitude, it might decrease, or the direction of motion might change. It depends upon how the force is being applied. Okay, so it changes or tries to change the motion of the body. That is what will be the way in which we can define the force in the context of the Newton's laws. Okay, now as we go into the chapter, right, we'll discuss about what are the common types of forces and things like that. Okay, but let us look at the another property which will be coming in the context of the second law of motion, which is the Newton's second law of motion. Okay, that quantity or that property is what we call as linear momentum, which is the vector quantity. We will represent this by the symbol P. Why are we putting a bar? Because it is a vector. It's a very simple definition. So linear momentum is going to be a measure of impact that the body can create. Linear momentum is what? It's a measure of impact the body can create. For this, right, let us just think about a very common example. I am sure all of you guys would have been walking on the road. Okay, so think about it. If there is a very small mass moving object like a bicycle, okay, which is coming and hitting you, obviously what is the impact? You will feel some impact, but the impact will be what? Minimal. Why? Let us say the mass of the person plus the bicycle is, say for example, some 100 kg. This is moving at maybe some 5 meters per second. Cycle usually moves with a lesser speed. You will see a small impact. Whereas you can think about a car coming. Don't even imagine it, because it is going to be very dangerous. If a car is coming, maybe some of the cars might have even a weight of some, we should not use the word weight, particularly in physics. Why? Because in chemistry you can use mass and weight interchangeably. Like you say in some of the things, right, you will say what? Gram atomic mass or gram atomic weight. You will use the word interchangeably, but in physics we cannot do that. Okay, why? We will be able to understand the reason in this chapter only. Weight is actually defined as the gravitational force acting on the body. Weight is defined as what? The gravitational force acting on the body. Mass is the property of the matter. Mass is the property of the matter. Okay, so weight and mass will not be the same in the context of physics. So let us say the mass of this car is some 1000 kg. This is coming at a speed of maybe some 50 meters per second, like that. Now you imagine the impact. The impact is going to be what? Very high. Okay, it might cause really some fatal damages. But the point here is how we will measure this impact. The impact of a moving body, right? The impact a moving body can create when it is hitting something is measured by the linear momentum. So how do you measure it? It is measured as the product of mass with the velocity. So any moving body will have a mass and it will have velocity. The product of mass with velocity rate is what will be the linear momentum. Here you can see velocity is what? Vector. That is why the linear momentum is also vector. One more thing we can see, the velocity rate, it will be multiplied by a scalar here, mass. This is what? It is a positive scalar because mass can never be negative. Remember, we talked about it in the properties of vectors. If you take a vector, multiply the vector by a positive scalar, like you have a vector a bar, multiply the vector a bar by a positive scalar k, then the resulting vector, let us give the name b bar. Here if you multiply the a bar with a positive number, then the resulting vector which is coming b bar and a bar will be what? Will be in the same direction. B bar and a bar will be in the same direction, which means what? Here the linear momentum and velocity both will be in the same direction. Linear momentum and velocity both will be in the same direction. Okay, so this is what is the idea of the linear momentum. Now guys, one thing, whenever we come across a new physical quantity, I think I would have told you what is the first thing that we'll think about. What is the SI unit of this physical quantity and what is the dimensional formula for the physical quantity. We should never forget this. So from now onwards, in whichever chapter we are coming across a new physical quantity, even if I forget, right, you should be asking, sir, what is the SI unit of the physical quantity? What is the dimensional formula? We'll just do it here itself. Look at it. Mass. What is the mass SI unit? Kg. Velocity is what? Meter per second. So the SI unit of the linear momentum is what? Kg into meter per second. Now let us talk about the dimensional formula. How do you get the dimensional formula? Dimensional formula for the linear momentum, we have the equation, right? Mass into velocity. Mass means what is the dimensional formula? L, m. And what is the velocity dimensional formula? L t power minus 1. So what is the dimensional formula for the linear momentum? ml t power minus 1. What is the dimensional formula for the linear momentum? It is what? ml t power minus 1. Okay guys, so you have to keep making a note of it. So every time we see a new physical quantity, right, first thing we should get is what? What is the SI unit of the quantity? What is the dimensional formula? Okay guys, so if you have any doubts, keep asking. Let us just quickly attack this question. What is it? A man of mass 4 kg. This is a very straightforward question, not even JEE mains level. Okay, here we are doing the question just to get ourselves some familiarity with the formula. That's it. A man of mass 4 kg has a velocity 2I plus 3j minus k. This is what? The velocity in the component form. So what is this? Component form of the vector I, j, k component form. Okay, so you can see here the mass is in the SI unit and velocity is also in the SI unit. What is his linear momentum or what is his momentum? Straight formula question, right? What is it guys? You can just type the answer, m into v. M is what? 4 kg into 2I plus 3j minus k meter per second. What is it? 4 2s are 8. 8I plus 12j minus 4k kg meter per second. That's it. This is what is the momentum. If somebody is asking us what is the magnitude, what we are going to do? Root of I component square j component square plus k component square. What is it? I component square j component square plus k component square whole root. Okay, so this is how we will get the magnitude. We can do it. So here what we will do is, see 8 square can be written as what? 4 square into 2 square. Similarly 12 square can be written as what? 4 square into 3 square. Minus 4 whole square means what? 4 square only. So we will see that everywhere the 4 square is common, it will come out. Once it comes out the root, it will be what? 4. Here what is remaining? 2 square, 4. 3 square, 9 plus 1. What is it? 9 plus 1, 10, 14. So what is the final answer? The magnitude is what? 4 times root 14 kg meter per second. Check it guys. If you are looking for the magnitude, what should be the magnitude? 4 times root 14 kg meter per second. Okay. Is it clear? So this is how we are going to get the momentum. So we'll move on to the Newton's second law, because why are we learning about the momentum? Because we said the momentum is going to be useful in understanding the Newton's second law. So Newton's second law is the most important. Why? Because if you have to very bluntly put it right, the entire chapter of laws of motion is going to surround this law. Just on this one formula only, we are going to discuss the entire chapter. Okay, so what is this? The rate of change of linear momentum of a body is equal to the external force applied on the body. So if you look at the rate of change of linear momentum, means what? Change in the momentum value divided by the time taken. So this is what we are quantified as what? The external force, because force is the vector. We should keep that in mind. Now when we say rate of change of momentum, we can either have the average rate of change, which means what? Change in momentum by the time taken for a finite. This is what? The average rate of change. This will give us what is the average external force value. This will be giving us what is the average external force value. We can have the instantaneous. Means what? We take a very small time dt. In that small time, if the change in the momentum is dp, that also will be what? Very small. And like the way we have discussed, this rate of change of linear momentum, we cannot get it by using the normal approach, like the way we do it for the average value. We have to use either the differential approaches, or we have to use the graphical approach. If you have to get this instantaneous rate of change of momentum, right, we have to either use the differential approach or the graphical approach. This is going to be giving us what is the external force acting on the body at that instant of time. Okay, so we'll stick to this definition, because we are looking at what? At an instant, what is the force acting on the object. This is not going to be much useful. Okay, this one is not going to be much useful. Okay, unless we have a constant force. Okay, so what is a constant force? Like the way we say constant velocity means what? Velocity which will have same magnitude and same direction. Similarly, constant force means what? A force which will be having the same magnitude throughout and also the direction. Okay, in that case, the average rate of change also can be used. But otherwise, we'll be more interested in what? The instantaneous rate of change of momentum. That is going to be giving us what? It is going to be giving us the external force acting on the body at that instant. It is giving us what is the external force acting on the body at that instant. Okay, so this is about the Newton's second law. This is the the basic definition of the Newton's second law. Now in our lower standards, right, we might sometimes see that Newton's second law can be defined by using momentum, or it can be defined by using acceleration. Like that, we will see that there are two definitions, but actually there are no two definitions. There is only one definition, and this definition can be modified depending upon two scenarios. We are saying body. We are saying what? Body. So the body or object we are considering, right, can be having a fixed mass. Normally any body you take will have fixed mass, but sometimes the body or the object you are considering can have variable mass also. Like you think about one of the example that we'll anyway discuss in this chapter is rocket. When a rocket is propelling, right, what is going to happen? The gases are going to be exhausted. Where are the gases coming from? They are coming from the burning of the fuel which is there previously inside the rocket. Means as the rocket is moving forward, what is happening? The mass of the rocket is going to keep on decreasing, isn't it? Because the fuel is coming from where? It is coming from within the rocket only, no? So those kind of bodies are example of what? A variable mass objects. So when you look at an object or a body, it can have a fixed mass, which is the case in most of the situations, or we can have a body which is having variable mass, like I said, right, the example of the rocket. Now the Newton's second law can be modified the basic statement can be modified depending upon whether we are talking about the fixed mass object or we are talking about the variable mass object. Okay, so we will see what is the Newton's law of modification that we can do for an object having a fixed mass. We can also call it as what? A definite mass object. What we can call it as? We can call it as what? Definite mass object. Okay, now here we'll either look at that average formula or the instantaneous formula. What is the statement? External force acting on the object is equal to what? Rate of change of momentum. So here what is it going to be? External force is equal to what? Now remember, here rate of change of momentum means what? This is like final momentum minus initial momentum. What is final momentum means? M into final velocity, let's say V, minus initial momentum is what? M into U. Look at this, M is common. What is this? V minus U by delta T. What is it? This is the average acceleration, correct or not? So for a given finite time interval, what is the final velocity minus initial velocity time taken? It is what? Average acceleration. Okay, so that is what we have. So what is the conclusion? If the object is a definite mass object, then the force acting on the object will be equal to what? Mass times, because here mass is a constant, mass times acceleration of the object. It is what? Mass times acceleration of the object. Okay, now if the instantaneous formula is taken, look at this. So derivative of momentum is what? Mass into velocity. Here M is a constant, that is what we are saying, definite mass. So we are taking derivative, constants will come out, right? M into derivative of velocity. What is derivative of velocity means? Rate of change of velocity, derivative of velocity with respect to time. What is this? This is nothing but the instantaneous acceleration, right? If we take derivative of velocity function with respect to time, what is it going to give us? It will be giving us what is the instantaneous acceleration. So from both the formula we will get the same result. Force acting on the body is equal to what? Mass times acceleration of the body. Force acting on the body is equal to what? Mass times acceleration of the body. If you take at an instant of time means you will get the instantaneous relation between the force and the acceleration at that instant. You take the average acceleration means mass times average acceleration of the body will be equal to what? The average force. The average force acting on the body. Okay, so this is what is the Newton's second law for the definite mass object. So what is it that we will be able to conclude? Force acting on the body, external force. You have to keep in mind what is the force we are saying? External force. External force acting on the body is equal to what? Mass times acceleration of the body. What is it? Mass times acceleration of the body. Okay, so now we are keeping both these average formula and the instantaneous formula together so that we will understand that the second law basic definition, right, can be derived both as an average formula context as well as the instantaneous formula. Okay, now we will look at other scenario. What is the other scenario? When the mass will be changing. Okay, so when the mass is changing, if it is not a definite mass, then what we are going to have? We will have a different result. We will not be having this force is equal to mass times acceleration of the body. We will be having a different result. And you know what did we say? We are going to look at the result in case of systems like the rocket system. Okay, before we go to that variable mass system, what we'll do is we'll do some sample questions based on this definite mass kind of system. So what is the formula we have? Force acting on any object having a definite mass will be equal to what? Mass times acceleration of the object. So this is what we'll generally use as the Newton's second law statement in case of the definite mass objects. Okay, we'll look at this question. So here also these are very straightforward questions. A body of mass 2 kg is acted upon by a force 2I minus 4j plus 2k. Mass is in kilogram, SI unit. Force is in Newton, SI unit. What is the magnitude of acceleration generated? So what is it, guys? Force is equal to m into acceleration, right? Means here we are looking for what? Acceleration. Bring the mass to the left side. F bar by m is equal to what? A. Look at this. What is F bar given to us? 2y minus 4j plus 2k. This is in terms of Newton. Divided by what is the mass? 2 kg. So Newton itself is what? Kg meter per second square, right? So kg is cancelled. Here you will see that 2 ones, 2 twos. So what is it, guys? I minus 2j plus k meter per second square. This is what is the acceleration as a vector. But they are asking us what? The magnitude. Means what will be the magnitude? Root of, here what is I component? 1. J component is what? Minus 2. K component is also 1. So 1 square is 1. Minus 2, if you square it, means it will become what? 4. So what is it? Root 6. What is it, guys? You have to type. If you get the answer, means you have to type it. What is it? Root 6 meter per second square. What is the value? It is what? Root 6 meter per second square. Clear? So this is what is the acceleration generated inside that body. We look at one more question. A body of mass 3 kg is acted upon by 2 forces. So here we are having how many forces? 2 forces. Check it. Let us call them as what? F1 and F2. Both of them are having the same magnitude. What is the magnitude? 10 newtons. But they are acting with an angle between them. What is the angle between the 2 forces? 60 degrees. Find the net acceleration magnitude. Means what they're asking? They're asking what is the net acceleration magnitude. See, if there are multiple forces acting on the object, like in this case F1, F2, maybe you can have another force F3, maybe you can have one more force F4, like that. When we say external force, in case of multiple force acting on the body, right, what is it that we are going to consider? We are going to consider the total value of all the forces, means the resultant of all the external forces acting. That is what is the total external force. That's why in the statement what do we say? The total external force acting on the body. Means if there are multiple forces acting, then the total external force means what? It is the resultant or net or sum, whatever the word that we use, of all these forces. One thing that we need to keep in mind is when we say the resultant of the forces or the net of the forces or the sum of the forces, we are dealing here with what? Vectors. We are dealing with what? Vectors. So we have to be careful that we have to do the addition as per the vector laws. We cannot just add. In this case, right, there are 2 forces acting on the body. What are the 2 forces? 10 Newton, another is also what? 10 Newton. Can we straight away say that the total force acting on the body is 20 Newtons? No, right? Here, if you want to find what is the net external force, it is what? The resultant of these 2 forces. Look at it, guys. What is the resultant of the 2 vectors formula? If you have 2 vectors A and B with an angle theta between them, resultant formula, what is it? Resultant is equal to what? A square plus B square plus 2AB cos theta, correct? Here we have 2 forces, F1 and F2. Root of F1 square plus F2 square plus 2 F1 F2 cos theta. So what is it? F1 is 10, it is n square plus 10 square plus 2 into 10 into 10. What is theta here? Angle between them is what? Look at this. Both the forces are given as what? Co-initial vectors. Remember, this is also important. When we say angle between 2 vectors, we have to be careful. First, the vector should be represented as what? Co-initial vectors. So co-initial, they are already there. And what is the angle here? 60. So we are going to get cos 60. What is cos 60? Half. Means the 2 is cancelled. So 10 square plus 10 square plus 10 square. What is it? 3 into 10 square. So 10 square will come out. It will come out of the root, means it will be coming out as what? 10. So what is the net external force? It is what? 10 root 3 newtons. What is the next net external force? It is what? 10 root 3 newtons. Okay, guys. Now what they're asking? They're asking the net acceleration magnitude. So what will be the value? Net acceleration. A net is equal to what? the net external force divided by the mass. Already we have it right. F is equal to m into a means a is equal to f by m. So this net external force is 10 root 3 newtons divided by what is the mass of the body? 3 kgs. What is the mass of the body? 3 kg. Okay. So here we can do some mathematical simplification. 3 we can write as what? Root 3 into root 3. So 1 root 3 is cancelled. Check it, guys. Finally, what is the net acceleration? We have a 10 in the numerator. Denominator we have a root 3. Unit is going to be what? Meter per second square. SI unit. What is the unit here? It is what? Meter per second square. Clear, guys? So this is what is the net acceleration of the body. This is the net acceleration of the body. Okay. So as we said, the entire chapter is about what? The application of the Newton's second law, right? So here we have just taken some very two basic examples. But as we go into the further discussion, so we will see that how or in what different ways we can apply this Newton's second law in various contexts. Okay. So we will go to the other case of the Newton's second law. What is it? The case of the variable mass object. So what is the thing that we can generally remember? The moment we say the variable mass, we should remember this rocket. Okay, because it is going to be an example that we'll discuss. So look at it now. Variable mass. What is saying? Variable mass, right? So if you look at the instantaneous formula, what is it? The derivative of momentum. What is the external force acting on the body at an instant of time? What is the instantaneous formula? External force acting is equal to what? Rate of change of linear momentum. So look at this, guys. This is what? Derivative of mass times velocity. Here, you know what you have to keep in mind? Mass is variable. Velocity is also variable. Means this is like what? Remember, we have the derivative of this u into v type of function. What is it? U into v dash or v prime plus v into u dash or u prime. So remember, now we are talking about the things that we did in the basic math videos. The derivative of u into v type of function. What is it? U into v prime. V prime means what? Derivative of v plus v into u prime. U prime means what? U prime or u dash, whatever we call it. What is it? U into dv by dt plus v into du by dt, like that. Okay, so here the u is replaced by what? Mass. That's it. U is replaced by what? Mass. Look at this, guys. We'll apply the same formula. This is called as what? The product rule of derivative. What is it called as? Product rule of the derivative. So look at this. M into dv by dt plus v into dm by dt. This is the external force acting on the body. dv by dt means what? Rate of change of velocity is what? Acceleration. Plus v into dm by dt. You know what is this? This dm by dt represents what? This represents what? It represents rate of change of mass. What it represents? For that particular variable mass object, right? dm by dt means what? The rate at which the mass of the object is changing. So just keep a note of this result. We will use it when we go to the separately. We'll discuss about the rocket propulsion. We'll discuss about the rocket propulsion separately. In that case, we are going to talk about this formula again, and we'll see how we'll use the formula in the case of the rocket. Okay, guys. So here, this is how we'll have the Newton's second law, the final form, in case of the variable mass object. Okay. Okay, guys. So we'll move on to the third law of Newton's laws of motion. What is it? This is also called as the law of action reaction pair. What is it called as the law of action reaction pair? Okay, so what is this action reaction pair law, or the Newton's third law? It basically states, this is something that we are quite familiar, okay, and we use it in different context also. So what is it? We'll say for every reaction there is an equal and opposite reaction. So here there is a lot of meaning when we use the word equal and when we use the word opposite. When we say equal, we are talking in terms of the magnitude. If you have an action means what? This is referring to a force. If there is a force that is applied, then there is going to be a reaction, means what? There is going to be another force that will be existing, which will be equal in terms of magnitude but opposite in terms of direction. So this combination of forces, right, is what we call as the action reaction pair of forces. Like I said, right, so these are some of the common ways in which we will be talking about this action reaction pair. Like, if you kick the donkey, means the donkey will kick you back, okay. But I mean, this is a very jovial way of putting the Newton's third law. But let us look at what is it in the context of the action reaction pair. So what exactly we mean to say by the action reaction pair? Okay, so here if you look at an object A, take another object B. Let us say the object A is creating a force on object B. Okay, the force may be gravitational force, it may be magnetic force, it may be electrostatic force, it may be any type of force. Let us not discuss about the nature of the force. We are saying, A is creating a force on the object B. Then the B will in return create a force on object A, which will be equal in terms of magnitude. You can see forces will be equal in terms of magnitude. But what about the directions? The first force, if you want to give them some numbers, is in this case towards the left. What about this one? Towards the right. So the action reaction pair of forces, right, are acting on one different objects. So the action reaction pair of forces they don't act on same object, they will be acting on different objects. That is point one. Second point is, these action reaction pair of forces, right, they start together. See, generally, when we use the word action, we will think that, okay, that is the beginning and reaction will be the latter part. That is what the words will actually convey, right? So we'll say, okay, so you are reacting, means what? No, so it is always taken as, the one that is reciprocated or that is starting later. But here, we should not take the same meaning as it is, because it is not like, first A is acting a force and then B is starting to act the force on A, not like that. Both these action reaction pair will be starting together. Means if we just consider t is equal to 0 as the starting time, both of them are going to start together. Both of them are going to be starting together. And if they are ending, means both will also end together. Like say t is equal to n. They are ending means both will be ending together. Okay. So they will be existing for the same amount of time. So one thing is what? They will not act on the same object. And they will be starting together and also ending together. And when we use the word equal is referring to what? Magnitude, like this. The word opposite is referring to what? The directions part of this action reaction pair of forces. Okay. Now there is a greater meaning that the idea of action reaction pair of forces will convey. That is, in universe, right, we can never have isolated forces. So in universe, we can never have isolated forces. Means you cannot have an object A just acting a force and not having so you just cannot have action. You'll always have the reaction, which means what? Always the forces will happen in combination or pair. We can never have isolated forces. In the universe, we can never have the isolated force. So for any type of force, let us say there is a mass m1, another mass m2. If m1 is attracting m2, means m2 will attract m1 with the same amount of force. If there is a positive charge, another positive charge, first and second, let us number them. If the first charge is repelling, like charges, they will repel each other. Is repelling the second one, means second charge will repel the first one with a force of equal magnitude. You can see here, both will be having equal magnitude but opposite direction. Both will have equal magnitude but opposite in direction. Okay, so this is what is the idea of action reaction pair of forces that comes from where? The Newton's third law. For every action, right, we are going to have what? An equal in terms of magnitude and opposite in terms of direction. So you have a reaction force. Okay, so this is what we have to cover in today's session, and in the next session, right, we'll be starting with the idea of law of conservation of linear momentum. Okay, so what is the idea we're going to start in the next session? We'll start with the conservation of linear momentum principle, and we'll see how this is related to the Newton's laws, because everything we are going to discuss in the chapter, right, is going to be related to the Newton's laws. Okay, so conservation of linear momentum we'll study in this chapter. Again, we'll take a relook at it when we go to the system of particles. Okay, so we'll see in the next session, guys, and practice questions. So whatever the things we discussed, right, try to pick up some questions and practice along those models. Okay, we'll see in the next session.